Hi everybody, Mr. Gerard here, and we're going to talk real quickly about logarithm or logarithmic functions. The reason we're talking about logarithmic functions after having talked about exponential functions is because they're inverses. To undo an exponential function, we take the logarithm of the function and vice versa. To undo logarithms, we do exponentials. And so the first thing that's very, very important is this right here, this log base a of x equals y. If and only if, that's what this means. This little double arrow says if and only if a to the y equals x. And this is important for a couple reasons. Number one, it allows us to go from logarithmic form to exponential form by taking this, the base, to the exponent and saying that it's equal to x, what we were taking the log of. Likewise, if you have a to the y equals x, that's the same as log base a of x equals y. This right here, the a, is the base, and so we always talk about the base in the exponent or the exponential equation. We also talk about the base in the logarithm. This is what we take the log of, and that's what it's equal to when we do the exponential form. And then this y is the exponent in our exponential form. So the first thing that we'll do is we'll work on going back and forth between the two. For example, this says log base 10 of 100,000 equals 5, which is really the same as saying 10 to the 5th equals 100,000. We just went from the base 10, raised it to the exponent 5, and said it was equal to 100,000. Same thing here, 2 to the 3rd equals 8, because log base 2 of 8 equals 3. Now when we have the exponent, or the exponential form, now this is our base, the 2, all right? So we're going to say log base 2. Now just like we went across the equal sign here, we're going to go across the equal sign here and say log base 2 of 1/8 equals -3, because 2 to the -3rd equals 1/8. Same thing here, log base 5 of s equals r. We don't even need numbers, but here's our base. Go across the equal sign and then say it's equal to the exponent. 5 to the r equals s. So being able to go back and forth between those two is a very, very important skill, because it's going to help us solve things like this. When we start to evaluate logarithms, we have simple logarithms such as this, log base 3 of 27. Well, when I'm doing this, I say 3 to what power is equal to 27? Well, if I know my powers are 3, I know that 3 to the 1st is 3, 3 to the 2nd is 9, and 3 to the 3rd is 27. Therefore, 3 to the 3rd power is 27, so the log base 3 of 27 is equal to 3. And we can check by putting in an exponent form, 3 to the 3rd equals 27, which is what I have written down here. Here we have a log base 10 of 10,000. So again, I'm going to ask myself, 10 to what power is equal to 10,000? Well, if I look at this, if I remember my powers of 10 right, 10 squared is 100, 10 cubed is 1,000, and 10 to the 4th is 10,000. So this means that 10 to the 4th is 10,000, and log base 10 of 10,000 is equal to 4. This is where it starts to get a little trickier, because now I'm going to say 16 to what power is equal to 4? Well, I know the square root of 16 is 4. Oh wait, I remember now, 16 to the 1/2 power, because square rooting something is the same as taking it to the 1/2. That's equal to 4. And so 16 to the 1/2 power is 4, so log base 16 of 4 is 1/2. Again, we can check by saying 16 to the 1/2 power equals 4, and that helps out a lot. Here we have log base 1/2 equals 8. Not quite sure, but I could say 1/2 to what power is equal to 8. When I start thinking about 2 or 1/2, I could say, well, 1/2 to the 2nd is 1/4, 1/2 to the 3rd is 1/8, but I don't want 1/8, I want 8. So what could I do to make the 8 go on top and the 1 go on the bottom? Negative exponents. So I say 1/2 to the negative third equals 8. If you had trouble with that, you could say, okay, well, that goes on the bottom now, and you have 1 over 1/8 on the bottom, and then that comes up to the top. So 1/2 to the negative third equals 8, and that all works out nicely there. Now, when we start to graph logarithms, we're going to take a look at something such as y equals the log base 2 of x. We've worked a lot with y equals 2 to the x for an exponential function, and these are just the decimal approximates, 1/8, 1/4, 1/2, then 0, 1, 1, 2, 2, 4, and 3, 8. And you can see those points are already plotted there. Because we know logarithms and exponential functions are inverses, we know that we can switch x and y. And so to switch x and y, I'm just going to say, well, 1/8, negative 3. The point negative 3, 1/8 becomes 1/8, negative 3. The point negative 2, 1/4 becomes 1/4, negative 2. The point negative 1, 1/2 becomes 1/2, negative 1. The point 0, 1 becomes 1, 0. The point 1, 2 becomes 2, 1. The point 2, 4 becomes 4, 2. And the point 3, 8 becomes 8, 3. Now when I go to plot these points, here's 1/8, negative 3. It's about right there. 1/4, negative 2, right about there. 1/2, negative 1, about there. 1, 0, oops, it's a little bit off here. So this would be a little bit more over this way. More over this way, more over this way. And then 1, 0, 2, 1, 4, 2, and 8, 3. And if I connect these dots like that, there's my graph of the exponential function. And there's one other important part about this, because if you remember, in our exponential function, we have a horizontal asymptote at y equals 0. Well, in our logarithmic function, we now have a vertical asymptote at x equals 0. And what this does is it allows us to change the domain and range a little bit. The domain now is 0 to infinity, whereas the range is negative infinity to infinity. And if you think about exponential functions, with exponential functions, the domain was all real numbers. The range was 0 to infinity. And so again, domain deals with x, range with y. So down here we switch the x and the y, and now this is my x and this is my y. You can see how the domain and ranges also flip. And so that's very important to understand. This also allows us to take another domain rule, and that domain rule is that you cannot take the log of 0 or a negative. So you can only log positive numbers. So now we have domain rule number 3. You can only log positive numbers. Couple special logarithms that we'll see are when we have the base 10. And when we have the base 10, that's called a common logarithm. And so we just write log of x. So if you just see log of x with no base, you know the base is 10. Likewise, if I said, what is the log of 100, you'd say 10 to what power is 100, and that would be equal to 2. The other special logarithm we have is the natural logarithm, and that's the log base e of x. E is a special number. We used it in continuous growth, and it occurs a lot in nature, and therefore we call it the natural logarithm. Why is it ln and n instead of nl? Good question. I don't know, but I do know that log base e of x is equal to the natural log of x. So if we see this, now we're thinking base e. And then a few last log properties here kind of go in what we're talking about before, where if you think about these in terms of exponential terms, they should make sense. For example, b to the 0 is always 1. So if we're saying log base b of 1, that will always be 0. B to the first is always b. And so log base b of b is always 1. b to the x always equal b to the x. And therefore, log base b of b to the x is always x. And then this is a kind of funny one to think about, but if you have b to the log base b of x, that's also x. And these are the inverse properties here. If we use common logs or natural logs, same idea. Log of 1 is 0, log of 10 is 1, log of 10 to the x is x, and 10 to the log of x is also equal x. Natural log of 1 is 0, natural log of e is 1, natural log of e to the x is x, and e to the natural log of x is also x. And so those are just some of the brief overview properties of logarithms and how to evaluate some of them and how to graph some of them. So I hope you learned something, and we'll talk more about this tomorrow.